those are the two issues that we are going to talk about today, because those are really big issues, but those are also more sophisticated issues. So most people who are early in their understanding of econometric issues, they don't get exposed to these. And even very sophisticated users, they also don't understand the nuances and the complexities that are involved in these issues, to how to understand and how to address those problems. Okay? So keep that in mind. It may be you follow that, or it may be that you get some exposure to these issues. So I'm not be getting into the mathematical part of it, but understanding the conceptual part of it, that, okay, what are these different problems, why they occur, and how to address these problems. Okay? So if you think about endogeneity, that what we call endogeneity, and I will tell you that there are three different types of endogeneity. People will refer them as in the same box without understanding the differences between those different types of endogeneity. But let me just give them some kind of like a arbitrary classification names. So I'm just calling them type A, type B, type C, because if I would have given them type 1, type 2, then it will trigger a different thought. Okay? You'll start thinking about type 1 error, type 2 error. So I just gave a name, something different, so that you don't get confused. Okay? So the type 1 endogeneity occurs when the two kinds of issues might be there. Okay? One is there is an important variable that is missing from your model. Okay? If you remember, we did like on day 2, day 3, we had built a data set, and then we were trying to estimate the parameters. And if we had not included some of the variables that should have been included in the model, you would have seen that how biased our coefficients were. Okay? Because we had the benefit of knowing the true parameters, that okay, what are the true parameters, so we could see that how biased those estimates could be if one of the variables that should be in the model is not there. Okay? So you have seen the effect of that, and you can also see it. Okay? So you go there, go back to the same model, and see if there is a variable that is significant because it's part of the original data set that we built. And if you exclude one of those variables from the model, estimate the parameters, and then you can see that how far off they are. Okay? Then there are the other two types of problem happens, which we call a sample selection problem. Okay? So there was one economist whose name was Hetman. He was given Nobel Prize for solving this problem. So it was a very big issue. People were not aware of that this is an issue in estimating the parameters, and he identified the problem. He found a solution for the problem, so and he was given a Nobel Prize for that. Okay? So that's you can understand it's a serious issue. And I'll go one by one all of those, like what those three types are. Okay? The third one is, which I'm calling type C. This happens when the assignment to any experiment is not random. Remember, we were talking about that, let's say, effect of mother's smoking during pregnancy and how that impacts or might impact the weight of the children. Okay? Now, you can see that it's kind of a problem where you cannot randomly assign mothers to say that, okay, you will be smoking and you will not be smoking, and we can have a random assignment to two groups, okay, the treatment group and a not treatment group. So those are the situations where you know there are two groups. There are people or subjects who have received a treatment, and there are another group which has not received the treatment. So we know the differences between those, but we also know that this was not a random assignment. That's one problem. The second, the more advanced development that has come in trying to address this issue is that what would have happened if the women who actually smoke had chosen not to smoke? What would have the outcome been? And this women who chose not to smoke, what would have happened if those same women had actually got into smoking? So those are called counterfactuals. So now we use econometric techniques to create those situations, because you can observe only one of the two states for any given subject, either a woman who smoke or a woman who did not smoke. You could not observe both these states. While it is possible that anybody could have gone to one or the other, but you will be able to observe only one of the two, not both. So how to actually know what this person or subject would have got if the person has chosen to be on the other group? Okay? And that's what we call counterfactuals. Okay? So let's go one by one, all these three, and I'll talk more about it. Okay. So you know that we already kind of talked about that the type 1 endogeneity occurs when there is a variable that should be in the model, but that's not in the model. So it leads to a situation which we call omitted variable problem. Okay? So the omitted variable problem, if you think about what is happening in this, so this is the true model. In the true model, the expectation, the mean expectation of the error is 0. That's in the true model, that's what you would expect about the mean of the error term. Okay? Now let's look at the second situation. So what we did it in this second equation, we are dropping the x3 variable. Okay? So we are making the variable x3 as the omitted variable. Okay? So now look at how the equation will become, because we removed x3 from the equation. So the second equation will be simply y is equal to alpha plus beta 1 x1, beta 2 x2, and then the error term. And we know by construction that this error term is actually capturing two things. Okay? It is capturing the error here plus this coefficient and its parameter as well. Okay? It's a sum of those two. That would be what the error term will be in this second equation. Okay? That's what would be. Now, in this second one, the expectation of the error term will be, with some little bit of math, it will be equal to this coefficient beta 3 and the expectation of x3 given x1 and x2. Okay? That would be now the expectation of the error term in the second equation. Now, so we are trying to figure out when this omitting this variable will be a problem and when it is not a problem. But that's what we are trying to do. Okay? So we know that there will be variables that we probably don't know because we don't know the true model. Okay? So there always will be a variable that is omitted. In any practical situation, in any model, there will be variables that will be omitted. Now, we want to find out when that would become a problem and when that would not be a problem. That's what we're trying to do. So if you look at what the omitted variable is doing, it is simultaneously impacting two things. Okay? It is impacting the error term as well as the dependent variable. Okay? Both the dependent variables you can see here, this was the variable we omitted. Okay? It is related to the outcome variable by definition in the model that is impacting. So it is impacting the outcome variable, and the omitted variable is now also impacting the error term. So because of that, our estimates will not be unbiased. So only condition it can be unbiased if this term is 0. Okay? So when that will be 0, okay? It will be 0 if beta 3 is 0. Okay? So if the beta 3 is 0, that will be 0. It doesn't matter what is the inside because it's a product of beta 3 with something. So if the product of 2, 1 is 0, it doesn't matter what. So if beta 3 is 0, then the expectation of the mean of the error term will be still 0. We are fine. Okay? So if beta 3 is 0, it doesn't matter. Omitting that variable will not be a problem. Okay? The second is the x3 is the correlation between x3 and x1, x2 is 0. Okay? It's not correlated with the other variables that are in the model. So which are the variables in the model? X1 and x2. Okay? So the variable that you have omitted, if that variable is not correlated with the variables that are in the model, x1 or x2, then it won't be still a problem. Okay? So if either of those two conditions satisfy, okay, the omitted variable's coefficient is 0. It, in a very simple language, what it means is it is not affecting the outcome variable. That's what the beta 3 0 means. Right? So beta 3 is 0 means it is not impacting the outcome variable. So it does not matter if you omit a variable that is not affecting your outcome variable. Okay? So it's not a big deal. But the second part, okay, if the x3, the variable that we have omitted, if it is not correlated with the variables that are in the model. Okay? So x1 and x2 are in the model. And if it is not correlated with those, then this endogeneity will not be a problem. Means omitting that variable will not create any bias in your estimates. The estimates will be efficient still. So it wouldn't be any problem. What if that's not the case? Okay? So how to solve that problem? If we have omitted a variable, so we want to know how to find out whether we have omitted a variable or not. Okay? That's the first part that we need to know, because we don't know the true model. So we need to know that, okay, these are the ones that I'm looking at, considering that they were going to impact my dependent variable. But I don't know what are the other possible potential variables that could impact the outcome variable. So how do I know that what I have omitted is really impacting my estimates in a way that it's an undesirable effect on it? Okay? So that's what the goal is, to find out whether this is a problem that I should worry about. And then the second thing will be, okay, if this is a problem, I need to worry about how to solve that problem. Okay? So those are the two things we'll talk about in the next one. And before I get to the next one, it's within the same type A, there is another type of endogeneity happens, is which we call one of the predictor variable is endogenous, because the solution for those two are the same. So I'm grouping those two types of endogeneity under type 1A. Okay, so that because the solutions is same for both of those, so we can look at it. Okay. So what we mean by that, I have a model. Okay? Let's say we have x1, x2, x3 are the predictors in the model, and one of those, or more than one, is what we call an endogenous variable. Okay? So now the question is, what we mean by an endogenous variable? Okay? So what the endogenous variable means, that the covariance between that variable, the variables that are in your model, and the error term is not 0. Okay? So if the covariance between the variables that are in your model, that you are considering that these are my hypothesized variables, and I'm looking at those, and the error term, if those two are, the covariance between those two is not 0, then that particular predictor or independent variable is an endogenous variable. Okay? So once we know that those are the two situations, okay, we kind of looked at. Now, how to actually solve this? To address both of these, we require what we call instruments. Okay. Now, the instruments are some additional predictors with some special property. Okay. So we need to know what is that special property. So we need to look for some new variables. Okay. And then we'll look at what kind of variables we have to look for, which we would call them instruments. Okay. So we need some additional instruments to solve this problem, that we have an omitted variable that should not be omitted, or in the model we have a variable that is endogenous. Okay. So we need to find a set of variable. At least if we have one endogenous variable, we need to have at least one new variable, okay, which we call instrument. And we can also at times use some of the other variables that are in the model, already in the model. They can also be reused as an instrument. Okay? So a given variable that in our model can play two roles. Okay? One role is of directly predicting the y, the outcome, the dependent variable, and that's the reason they are in our model. And a secondary role they can also play, that they can be one part of that instruments that we are looking for. So, but in order to have the valid instruments, among those variables, at least one should be the one that is not in the main model. So we are looking at two equations. Right? So one equation is the main equation, and there will be, now we are building another equation using the instruments that we are going to look for. So now the question is, what kind of property those new variables should have, so that we can say, okay, we have found the kind of instrument that we need, which will solve this problem. Okay? So the instrument or additional variables with two properties. Okay? The first property is that they are related with the omitted variable or the endogenous variable. Okay? So they, what we call, those instruments are relevant. Okay? They will be relevant if they are correlated with the variables that are endogenous in our model. Okay? But those variables are also valid in a sense that there is no, the covariance with the new variables we are looking, and the error term is. So two conditions. So we need to look for some new variables that meet these conditions. Okay? Let's say you have x1, x2, x3. You have 3. Okay? And let's say x3 is the one that is endogenous. So now we need a new variable, x4 or x5, which you can call. Okay? That x4 should have a property that it is related with x3, okay? But it is not related with the dependent variable. Do you follow that? So we need to look for a new variable that is related to the variable that is a problem variable in our case, and it's not related to our primary dependent variable. If that new variable meets this requirement, that it is related with the problem child but not with the dependent variable. Okay? So as long as we meet this situation, we have got the perfect. Okay? So obviously in real world we may not find an ideal variable that meets perfectly this conditions. Okay? Yes. Because we are not predicting the dependent variable with this. Okay? So as I said, we are going to have two equations. Okay? So let's assume that this x3 is the one which is a problem. Okay? Now what I'm saying is, if we can find a new variable, okay, that can, let's say we are calling that new variable right now z, that is related with this one, okay, but not related with this, okay, then it will solve the problem that we can substitute x3 with the z in the second equation. Okay, so that's the goal, that we are looking for a candidate that we can actually substitute x3 with, that is related with x3, so that's why it's relevant. Okay, so we want to, like, we can just take any variable. Okay, so it has to be related with the variable that we want to replace, but it should not be related with our outcome variable. Then it becomes a valid instrument. Okay, if it is also the same, then it's not solving the problem. It will become another endogenous variable. So if you replace an endogenous variable with another endogenous variable, then it does not solve the problem. Okay, so that makes it exogenous in that sense. Okay? So those are the two criteria that we should meet, that the covariance between the x and the z is not 0. That means it's relevant. It can predict the problem variable. And the covariance between the z, the instrument, and the error term is 0. Okay? So as long as it makes it what we call exogenous. Okay? So a variable that is endogenous, then this covariance will not be 0. Okay? So there is an error. Okay, this should not. This should be 0. Okay? Yeah, this should be 0. So let me make the correction here. Okay. Just make that correction. Okay, so exogenous, that covariance should be 0. Then only it becomes exogenous. Okay, and it is relevant if these two are related. Okay, so that's the covariance between those two is not 0. Okay, do you follow me? Okay. Yes, please go ahead. That's what it does. That's the explanation is given here. Okay, so that's the whole problem. Okay? The mean expectation. Did you follow this equation too? Were you listening? Okay. Yes. So if in the fundamental assumption the fundamental assumption in the ordinary least square is the expectation of the error term is 0. Okay, that is the requirement. You follow that? Now, if we remove our variable that should be in the model, what the error term becomes now? The error term is representing this plus this. First, understand. You asked me why that is a problem. Didn't you say that? Okay. I'm explaining to you why that is a problem. Okay? And then we have to, what's the way to identify that there is something that we are missing, which is vitiating our estimates. Okay? That's what we would know from our estimate, that whether we are missing something that we cannot afford to miss. That is how the problem. So how to diagnose? First, you have to understand what is the problem. That's what you are asking. And you are asking why that is the problem. Isn't you are asking? That's what your question. Okay? So don't change the question when you get the answer. Okay? So your question was that why x3, if it is related with the error term, why that is a problem. That was your question. Okay? Now did you get your answer? Why that is a problem? Did you get the answer or you didn't get the answer? Okay, so what does it mean here? So do you know little bit basics of the ordinary least square regression? Do you know that the mean expectation of the error term is 0 for this equation to be unbiased? You know that, okay? you can follow this thing that if we replace these two together with a new error term, now the new error term is sum of these two because x3 is removed from that. Do you follow that much? Okay. Now that means the error term is not 0 anymore. The expectation of the error term is not 0 unless this is 0, beta 3 is 0. Do you follow that much? Okay. Yeah. So that is the, so now do you know why moving x3 from the model is a problem? Forget about whether what it is becoming. You have to understand only this much, that okay, what happens if the x3 is related with the error term and we do not include x3 in our model? Do you follow that? Okay, is your problem solved or you still not solved? You didn't understand any of it eventually. Okay, so yeah, you can go and read more about that. So now the question is, there are two questions we are facing. Okay, the first is knowing when is this is a problem. Okay, when are we facing, when we have a variable that's endogenous in our predictor, or we have an omitted variable. So we have to identify that situation when that is a problem. And once we identify the problem, how to find, and let's say we are looking for an instrument, we have to test whether the instrument we have found is a valid instrument or not. Okay? So those are the two conditions. So once we detect the problem, then we have to look at is this problem a significant problem for us for the estimate. If the answer is yes, it is a problem and it is affecting our estimates. So it means we need instruments. So we look for instruments, then we find an instrument, and now we have to see that can we use this as an instrument or not? Is it meeting our requirements? Okay, so if you find that yes, we have found this new what we're calling instrument, okay, and it is a relevant because it is related with the variables we are having problems with, and it is not related with our dependent variable, so it's exogenous in that. Okay, so those are the two requirements. Let's go to the next part. Okay, so here I am just going to show you a little bit of that, just a sample of how much including or excluding a variable, to what extent it can affect the estimates. Okay, excuse me, can you get somebody's help because it's not focused again today. Yesterday the focus was better, and I don't think people can actually see. Yeah, here. So again, you see on the top here. So for demonstrating these issues, it's always good to create something by yourself. Okay, so you know what's the true model. Okay, what are the variables that should be in the model, and if they are, what should be their value. Okay, and then we can test if they are not included, how much the problem being created, how significant and how big is the problem that they are creating. Okay, so here we are building a data set. Okay, in this data set we already. I think it's better now. Can you see from the back? Yeah, so there is something there, like it was yesterday again in the beginning, it was not focused, was not on. Okay, so it's I think, can you see in the back, sir? Okay, so it's fine. So we have just created a variable which we are calling y here in this, using two variables that were already in our system, x1 and x2. And I'm using a combination of x1 and x2 and throwing in some random error in the mix. Okay, so that it's not fully determined. The y is not fully determined by x1 and x2. So I'm throwing in some error term. So this is how this model is created. We have now it's okay. Now it's working fine. Okay, yeah. So x1 is 2.567. Okay, that should be the true value coefficient of x1. And the true value of x2, the coefficient for x2, the beta 2, is 3.179. Okay. Now let's, so we built it, and now estimate, okay, keeping both of them. Then you see that how close and how far away the estimates are. So now you see here, the x1 coefficient is minus, so there is a minus here too, okay, yeah. So there is a minus here. So x1 we got minus 2.568054, okay, and you can see it's kind of close enough with the original or the true parameter, okay, which was minus 2.567. Okay. Now if you look at the second one, x2 here, so we estimated it 3.18049, and the true parameter was 3.179. Okay, so you can see that it's close, which is maybe reasonable, okay, because we built pretty much the perfect possible model. There were two predictors, and we got both of those predictors in the model because there was some error term added in, so it will be a little bit away. If that error term was not there, it will perfectly predict that. Okay, so now let's get to the, now what happens if we omit one of these two. So the omitted variable problem, how it impacts. Okay, so now we dropped x2. Okay, let's say we are looking at a model. We know the dependent variable is y. From our literature review, we found that x1 should be a variable that it should impact our variable y. Obviously, we don't know what are the other variables, and we didn't know the x2 was something that should have been in it. Okay. Now, if you look at, we estimated it. Okay, it's a very significant. X1 is highly significant. The t value is 14.72, so it's very significant. But what about the estimate? Is it biased or unbiased? It's heavily biased. Okay. So how do you know that's biased? Okay. Yeah, and we also know what is the true value. Okay, because we built the model. Okay. So we built the model, so we know that what is the true value. Okay, which was minus 2.17 or something in that range. Okay, so we know that how far off it is, even though it's still significant. But if that's all we care about, we would probably run with this. So we got our model, and we found the important predictor and all of that. So, but this is what we mean by the omitted variable bias. So now you understand that if a variable that is related and that variable y, that is a problem. Okay. So that is how this problem happens, which we call an omitted variable bias. So I just kind of put those two in the tabular form. Okay. So the results of those two, we estimated two models. I call the first model M1, the second model M2. In the first model, both x1 and x2 are there. And in the second model, only x1 is there, x2 is dropped. So I'm putting these two and in a tabular form, both the results in how you will probably put it in a paper or somewhere. So that's how just organize those two. You can see the x1 is in the first model minus 2.568. In the second one, it becomes minus 1.062. So it retains the sign, it retains the significance, but the estimate is heavily biased. Okay, so we are sort of underestimating by 50% in the omitted variable model. Okay. So I had created an instrument. Okay. So for some reason there was another slide there, and it's missing. But there was another variable I created, which was manually created. Okay, so which was related to x2, the instrument, that because x2 was the one omitted. Okay, and estimated what we call in two ways. Okay, one was the manual, and the other was using the stata. Okay? So in the manual procedure, what we do, we predict the probability of the x2. Okay? We predict x2, and then use the predicted probability in the second equation. Okay? That's how it is done. And this, now in the equation, there is estimate. So we are estimating x3 using the z, that is the instrument. We predict x3, okay? And then use that, which we call, and here we are including those two. So it's a manually, and there is a stata procedure. And then also I estimated the same using what we call the structural equation modeling, okay? So using that technique, now you will see how the estimates have improved with this, the use of the instrument, okay? I'll explain a little bit. There was one more slide, so I will just look for, there is another slide which is, for some reason, it's not there right now, okay? Now let's look at the second problem, which was the original problem that was identified by Hetman, and it was called the endogenous sample selection. Okay? Now, the endogenous sample selection is, so in the context this problem was identified, was like this. Okay? So there was an attempt to estimate the effect of the women's education on their wage rate. So the salary they are able to get, or the wages they are earning, that how their education is impacting their wages. Okay? So now you will see the problem looks like a simple problem. Okay? So you have a sample of women. You are trying to estimate that how the level of education impacts their wages or the salary that they are getting. Okay? Now see what kind of problem it is there, built-in problem, which early on people did not understand, and they overlooked the problem, and the Hetman identified, mentioned it, that this is a problem. Okay? So now you see that when you are looking at, let's say you have 100 women in your sample. So there are some who are what we call housewife or stay-home women, okay? And then there are who are also working, and then they have a salary. Okay? So now if you, let's say you are collecting the data, so in your original sample you have 100 women, okay? But let's say only 40 or 50 or 60 of them are working. So you have wage information for only 50, 60 women that are working, okay? And the remaining one who are not working, obviously there is no wage information about them because they are not working. Okay? Now, if you are estimating the impact of their education, their family environment, and all of that on their salary, okay? That how many children they have, and whether she lives with her mother-in-law, because that can impact dramatically his salary, okay? Or not. Okay? So all this can have. Do you see that? Will there be problem if we don't worry about the women for whom we don't have their salary information because they are not working? So do you consider that would be a problem? What would you do? Okay? Let's say you have that situation. You're collecting the data. You have a sample of 100 women. You have full information about their family, their education, and all of those age and all of those important variables. Okay? And now you want to know that, okay, given that, what is the level of education, how it is impacting their salary. Okay? So you know their education, whether they are graduate, PhD, high school, intermediate, primary school, like whatever. I mean, you have all kinds of subjects with wide variety of education, and your goal is to kind of figure out that, okay, how the education is impacting their wages. So obviously there are stay-home women in that, and they are not working, so you don't have their wage information, and you need to estimate it. Okay? So how would you go about doing it? So the way Hetman identified it, the underlying logic was this, okay? That probably that the women who are not participating in the labor market are thinking, expecting that if they become part of the labor market, their wage may be less than what they want. Okay, so if the wage is less than what they want, then they are not going to accept that, and they will choose to stay away. Okay, so it means that there is a threshold level of wage that unless it meets that requirement, we will not be able to observe it, because if it is less than that, people will choose to stay back and not go and work because they don't think it's not worth it. Okay, so that was, I mean, it may not be necessarily fully true for everyone, but that was the logic. Okay, the whole thing that, okay, we are not observing our dependent variable because our subjects are looking at or expecting that information, and based on that expectation, they are making a choice. Okay, the choice is to be in or to be out. Okay, and we will observe why only when they have chosen to be in. Do you follow that? So that's how this whole problem was conceptualized, that we have the original equation y is such that beta x plus e, but it will be observed only, but it is a function of another variable, which we call a selection variable. Right? So selection variable has two values, 1 or 0. Means there is another decision is being made. The decision is to be part of the labor force or not. And we will observe y only when that choice, which is we are calling with D here, is 1. Okay, that they have decided to be in, then only we are going to observe it. Okay, so there we are treating y as a latent variable. Okay, there is a part of the y when it is below that level, which we are calling the threshold level, people are choosing not to participate in that. So the D becomes the variable, the dichotomous variable, or what we call a choice variable. Okay? The choice variable is that people are choosing to be in or out. They have other reasons. We have to find out, okay, what are the factors which we can actually use to predict whether they are going to be in or out. Okay? So if we can figure out something, some other variable that can predict, okay, that whether you will be in or out, then we can use that information to now estimate, and including the probability of choice being 1. Okay? So you remember that we can use the probit or the logit model when we have a dichotomous dependent variable. So now this equation becomes 2 equation. Okay? So we have to estimate 2 equations now. The first equation is the main equation that we have. Okay? The second equation is the choice equation, where we are representing here with the D. So there are 2 different dependent variable. Okay? So one dependent variable is a choice variable, which just takes 1 or 0. If it is 1, then the y will be observed. If it is 0, y will not be observed. Okay? So now the task becomes how to predict D. So if we can predict D, we can include that probability in our main equation and now estimate it using that. You follow that? So we are looking at a data, is just kind of giving you some information about, so they are looking at the women, where they are located, what's their age, what's their education, whether they are married or not, and how many children they have. Okay, so that's the kind of like just giving you the data file here. We are looking, the age is from 20 to 59. Education is the number of school years that they have gone through. So it's from 10 to 20 years of education. Whether they are married or not, so it's a dichotomous 0 or 1, and whether they have children and how many children they have. So it can be from 0 to 5. Okay, so that's just the data file that we are going to use to do this. Okay. Now, it is so the first part is just showing you that the information about the descriptive statistics and on the right side it is just describing those variables. Okay? So if you have a data file and you command des or describe, you will see the right side thing, okay? Which will, if those variables are labeled, we call, in your do file you might have seen that we had a command label var, and there was a name with some quotes, and the quotes would show up in a red color, okay, anytime. So Stata knows what kind of thing you are playing with, okay? So the moment it sees the quotes, it knows that, okay, it's just a name, and you can write anything inside those. It doesn't worry about that. Or if you put a star in front of anything, it's an instruction, it will know it's an instruction, and it doesn't have to worry about it. It's not start looking for a command there, okay? It knows that, okay, ignore that, okay? So that's what, so it's a label var. So what is, the label is, okay, put a definition of this variable, okay? So I want a label, okay? So label var is, I'm asking it to label the variable, and then quotes, and then will be the name, whatever name we are giving, however we are describing. So many people, you will see that their variable names will be like this long, okay? So instead of, so what it is, that you want to have the variable name small, okay, so that you have to type less, while the description could be long. That is, whatever is the variable that you can define and take whatever length you need to actually define. But don't use that in place of the name, okay? So instead of saying that, okay, number of children a woman has, okay, somebody can write that variable, okay? So a variable name could be long, okay? So the number of children a woman has. So instead of using that, say children, okay? Maybe even small, C is fine too, okay? Just use C for children and define C, label C, okay? So if you just write C for that, you have to type very little for that, okay? In your do file, and only one time you have to define the variable. So anytime you want to see what this variable is, you type describe, it will describe for you, and you don't have to type too much, okay? So that's the little bit of an efficiency-oriented writing the do file, okay? And some discipline that how you maintain that. So that's what it does on the right side. On the left side, it's simply describing, okay? So now we are here running what we call the Hetman selection model, okay? In the selection model, we have, these are the equation trying to predict whether a woman will participate, will say yes to work or not, okay? And they are using married, whether she's married or not, children, how many children, and education and age. And now they are estimating in the primary equation the effect of education on the wages, okay? So this is, again, you can do it manually, or you can do using the Hetman command from the Stata itself. So if you want to do manually, we calculate what is called the inverse Mills ratio, and because it's not a variable that is observed, it is estimated. So anything that is estimated and now it is being used as a predictor in the main equation, the estimated standard errors need to be adjusted, okay? Because there is a measurement error in one of the predictors. So what happens when we do it manually? It's very complex formula to actually calculate the modified standard errors. So while you calculating the inverse Mills ratio directly is easy, including it as one of the predictors in the model is easy, but adjusting these standard errors is very complex, okay? So my advice will be that you don't do for your, okay? You can do it manually just for you, okay? If I calculate myself what it will be, but use a program because they have done the calculation that, okay, the moment you are using that, how the standard errors needs to be adjusted. They have calculated it and let them take care of it for you. But you should know that what exactly is happening, what the Hetman command is doing here, okay? So Hetman command is doing, it is executing two equations at one time, okay? So it is using two equations. One is the choice, predicting whether a woman decides to become a part of the labor force or not. If she decides to be part, then we will see the wage. If she has decided not to participate, that means she is stay home. We will not have a dependent variable information. Okay? So this is what we call a sample selection issue. The sample selection is, and it becomes a problem when the choice is endogenous. Okay? Then it becomes a problem because the choice is, if the choice is based on the expectation of the wage. Okay? So it is also possible that somebody has decided not to work for some other reason, not related to the wage issue. That, okay, if I work, how much money I will earn. And if that is influencing the decision, then it creates a problem because it becomes an endogenous sample selection. If the decision not to work is impacted by some other considerations, not the expectation of the salary that we are trying to, then it's not a problem. Okay? Even if you don't observe it, it's not going to make your estimates biased. Okay? It becomes a problem. So many times people will say, oh, you have a sample selection. Okay? Now you need to look at when sample selection becomes a problem. Okay? So the sample selection becomes a problem when the selection is happening as a function of the expectation of our dependent variable. So it becomes an endogenous variable that the choice we need to now predict. So you see that how we were doing in the previous one. There was a variable which we dropped, which is an omitted variable. Okay, remember that we said that we need to find a variable that can predict that omitted variable. Okay, so now in this case, visualize the situation like this. Okay, so the original model has decision to work is another variable that is not included in the model. Okay, so if you, let's say you create another new variable, okay, and you decision to work, and it can take two values, okay, 1 or 0. Every time you see that the wage information is there, you put it 1, okay, that the decision to work is yes. And anytime you see that the wage is missing, you say 0. Okay? So now you will have full information in terms of observation of a variable that is omitted from the model, okay? which can take only two values, 1 or 0. And we know that when it is taking 1 and when it is taking 0. It will take 1 every time the wage information is there. It will take 0 every time the wage information is missing. Now, remember how we did it. So we have a variable which was omitted. Now we needed to find an instrument that can predict this omitted variable. Okay, so that's what the Hetman is doing, is asking for instruments to that. Okay, decision to work. We are trying to predict using the number of children and married and all of those, that may those decisions have an impact on whether somebody wants to work or not. Okay, so using that, and now the number of children is, we are assuming that some of these are not dependent on the wage expectation. Okay, so those are like the decision to be married or not to be married is not driven by how much salary that women would get if she decides to work. Okay, so those are some of the requirements of that these should be exogenous. Okay, that these are the instruments that we have. These are exogenous, means the decision to marry or number of children. We are assuming that they are not also driven by what would be her salary if she decides to marry, okay? If she decides to participate in the labor force. Okay? So given that, this is how we are doing it. Okay? Everybody with me on this, what we are actually doing. So what the Stata is doing when we say Hetman this, and you tell what are the instruments, then it actually runs two equations. Okay? So equation 1 is the one which is the first one it does. Okay? It will run a probit model. Okay? Probit model, which is the dichotomous variable here, the decision to work, which you just created yourself, 1, 0. Okay? So this is the one that you are going to use, and you are using those married, education, and some. And you can see the education is one which is common in both the instrument equation. this, which we call a selection equation in Hetman language. So it is common in the selection equation, and it is also in so there are some that can show up in both the equations, but there are some like number of children and some of those we are not including in the wage equation. So we have two equations. One is a wage equation and the other is a selection equation. Selection and education is one variable which is common in both. We are using the education could be also impacting a decision to work. If the education is probably low, maybe a lady is less likely to work because education is low, but then, and if education is high, she may decide to work. Okay, so that's an important variable. The number of children and the marital status could be some of the other variables that can impact that whether somebody, a woman is choosing to work or not. So so manually what we are doing, we are predicting first the decision to work. That is one equation using the Probit model. Okay, then we compute an inverse Mills ratio. Okay, if we do that manually, and then use the inverse Mills ratio as a predictor, an additional predictor, a new predictor in our wage equation. Okay, to take care of that omitted variable problem that is in there, and it's not explicitly there, but we are making it now explicit. We are factoring the effect of that omitted variable in our wage equation. Okay, everybody with me on this, or you have any question? So D was the decision to work. Okay, so D was simply the decision to work. We created, like B has an Y, which was the wage, how much salary or wage of and D was simply the decision to work or not to work. Okay, and if D is 1, then we will know that there will be a wage information. When the D is 0, the wage will be missing. Okay? So you can see that how this works, and you can see the estimates that how if you ignore that problem and you don't ignore the problem, how much problem it creates. Okay, so now you can see that it has impact little bit. Okay, in this particular situation, we have a downward bias about the education. Okay, so you can see the effect of the education on the salary or the wages is expected is 0.897. Okay, so if the education increases by 1 year additional, the wage is increasing by 0.897 units. Okay, so that is the expectation if we had not incorporated this. So you can see that after we have incorporated that information, then the coefficient on the education has changed, but you have to be careful about estimating directly that what is the impact of education on the outcome, because education is showing up in two places. Okay, so there are now two equations, equation 1 and equation 2. So it is always better to let the data tell you that what is the effect. So you do the margins, it will calculate it for you, that it will consider both the equations. Okay, so if you try to do manually, you may not be able to do that. So it's always better to say, okay, because you have to just ask, they said, okay, I want to know the effect of education on this. You use the margins command, and it will give you the effect, because it is going to factor the effect that's showing up in equation 1 and equation 2. Okay, that. So at this time, we are only doing, so I have given you enough information that you are aware of the problem, okay, that when my research project has a sample selection problem. Okay, is there one, or is there not a problem? So you have to look at the data a little bit more carefully to understand, okay, that it is possible that somebody actually didn't even think about getting the wage information from women who are not working, because that information is not even relevant. Okay, so why would somebody go and ask them? So you will only go to the people who are working, and you'll get the education and rest of the information from only those women, okay, who are working, and then you'll run the estimates based on that. Okay, so now you see there would be a problem that the researcher will not be aware of the problem, because they just will think that, okay, I want to know that, okay, what is the the effect of education impacting, how it is impacting their salary or wages. So I go to the people who are working and ask them, what is your salary, what is your education, your family history, age, and all of that. And then I go back in my office and run that information and say, okay, this is how the level of education is impacting their wages. But you would see that you would not realize that there is another group of women who you have not included in your sample because their wage was missing. Now, and wage is your dependent variable. And then you have to think about, is it something to do with this salary? If it is, then it is a sample selection that you have to worry about. Okay? So just recognize this, that you have to look at your sampling strategy a little bit more carefully to understand the problem, okay? Especially if you use survey data. Okay? Because what happens with survey data, and a lot of people do that, okay, with the survey. And I feel bad when some of that comes and shows up on my table. Okay? Why? So somebody sent me 400 pages thick, hardbound thesis. Okay? So I was external examiner, and I see it's hardbound, okay? And I'm external advisor, examiner for that. So my job is to look at issues in that thesis and tell the person to actually address those issues. Okay? Now visualize the cost of all of that doing. That person has already has put 400 pages document, hardbound, printed, everything complete, and I'll feel guilty, isn't it? Like, I'm going to ask them, throw this, do this and that again. That's one part of it. The second part is that person has done a huge survey, okay? And now there is a huge problem in the sampling strategy in this sample. And I see that, nope, I can't trust this. You got it wrong. You cannot do this. You have to do survey and go and collect responses from this group. Now visualize the situation, okay? How hard it is to gather data using survey. If your survey design was not carefully thought, now you will have to go. Sometimes there is additional information that you could have got from the same respondents. Now, either you have to reach out to those people again. Let's say there may be some instrument that we can use or something is missing that should be included, or go to a completely new set of respondents and now collect and run this survey data one more time. Okay? So that's the reason if you are using survey data, you must be very, very thoughtful in your sampling strategy. Why? Because if you make a mistake in your sampling part, then everything that you have done is, first thing, is problematic, and the second thing, the cost of fixing that is very high. Okay? So if it, let's say, secondary data, and you are doing, and let's say you didn't include the GDP information about the India, let's say, or whatever you are doing, that I will ask you that, okay, you should include that control for the GDP information. Now, yeah, obviously the hardbound is a cost that has to be thrown out, okay? And that has happened many times, okay? That I'm not willing to sign on this unless you do these. I don't have time, first thing, to do these kind of stuff. But if I'm giving my time, it's a free time, okay? So if I'm giving my time, you have to follow what I'm saying. Okay? So you have to be very careful in terms of, if you are still working on toward your dissertation, that what are the things I have to be really careful, and the survey researcher have to be really, really careful. I've told many times that never go and settle for same respondents and get information on both your dependent variable and the independent variable. Okay? So, which you know the problem of what we call as common method bias, and typically people will come and say, okay, I did the Harmon's test and I did not find that the common method bias was there. Okay, no, the time has gone, and now people are not saying, okay, I'm nothing doing. Okay, I don't care about what you found. You need to have the respondents have to be different. Okay, plain and simple. So just be careful about that. Okay? So maybe let's take a break here, and then we will come back after 15 minutes. Okay?